What specific problem does your method address regarding the training data acquisition for language models, and why is it significant?
Our method addresses the challenge of acquiring training data for language models, LLMs, which traditionally relies on costly and time-consuming human-generated problem-solution pairs. This is significant because recent studies have shown that synthetic data can be generated using weaker but cheaper models, WC, instead of stronger, more expensive models, SE, allowing for a more scalable and efficient approach to data acquisition. By sampling more solutions from the WC model under a fixed compute budget, we achieve higher coverage and diversity in the generated data, which can lead to improved model performance. Our findings indicate that training on data from WC models can outperform training on data from SE models, suggesting a paradigm shift in how we approach data generation for LLMs. This method not only reduces costs, but also enhances the training process, making it more accessible and effective for developing advanced reasoning capabilities in LLMs.
How does the proposed method work? Illustrate the steps involved in your approach from data generation to model fine-tuning.
The proposed method involves several key steps, starting with data generation and culminating in model fine-tuning. First, we generate synthetic data by sampling multiple solutions for each reasoning question from a weaker but cheaper WC model, resulting in a dataset, D_G, that includes reasoning chains and final answers. This dataset is then filtered to retain only the solutions with correct final answers, creating a refined dataset, D_G. Next, we employ three distinct fine-tuning paradigms. 1. Knowledge distillation, where a student model learns from a stronger model. 2. Self-improvement, where a model learns from its own generated data. And 3. A novel approach called weak-to-strong improvement, W2SI, where a strong model is enhanced using synthetic data from a weaker model. Finally, we fine-tune the models on the filtered synthetic data from both the WC and stronger models, comparing their performance across various benchmarks to assess the effectiveness of the WC-generated data.
Can you provide a simple example to demonstrate how your method improves model performance using a weak model? Walk through the key steps with this example.
In our study, we demonstrate the effectiveness of using a weak model, WC, to improve model performance through a specific example involving the Gemma 2 family of models. We start by generating synthetic data using the Gemma 2-9b WC model, which allows us to produce 3 times more candidate solutions per problem compared to the Gemma 2-27b SE model at a fixed compute budget. For instance, when fine-tuning a student model, GEMMA7b, on data generated from the WC model, we observe a relative performance gain of 6% on the math dataset at a low sampling budget. This is achieved by leveraging the higher coverage, 11% more unique problems solved, and diversity, 86% more unique solutions, of the WC-generated data, despite its higher false positive rate, FPR. Ultimately, this example illustrates that training on the synthetic data from a weaker model can yield better performance than training on data from a stronger model, thereby establishing a new paradigm for model improvement.
What advantages does training with the WC model data offer over the SE model data in terms of coverage and diversity, and how do you quantify these benefits?
Training with the WC model data offers significant advantages over the SE model data in terms of both coverage and diversity. Specifically, the data generated from the Gemma 2-9b WC model outperforms the Gemma 2-27b SE model by achieving 11% higher coverage and 86% higher diversity at a low sampling budget for the math dataset. These benefits are quantified by measuring the number of unique problems solved, coverage, and the average number of unique correct solutions obtained per problem, diversity. For instance, at a high sampling budget, the WC model shows an increase in coverage and diversity by 6% and 125% respectively for the math dataset. This indicates that the WC model can generate a larger number of unique solutions, thereby enhancing the training data's utility for model fine-tuning.
How did you validate the effectiveness of your proposed method? Please describe the experimental design, datasets, and metrics you used to measure performance.
To validate the effectiveness of our proposed method, we conducted experiments using two reasoning datasets, Math and GSM-8K, each containing 7,500 training problems. We generated synthetic data using the GEMMA 2 models, specifically employing GEMMA 2 to 9b as the weaker model, WC, and GEMMA 2 to 27b as the stronger model, SE. Our experimental design involved three fine-tuning paradigms: Student LM fine-tuning, WCLM fine-tuning, and SELM fine-tuning, where we compared the performance of models trained on data from both WC and SE models. We measured performance using metrics such as Pass-It-1 accuracy, coverage, diversity, and false positive rate, FPR, with results indicating that models trained on WC-generated data consistently outperformed those trained on SE-generated data across various setups, achieving relative gains of up to 31.6%. This comprehensive evaluation demonstrated that sampling from a WC model can be more compute optimal than the traditional approach of using SE models.
What limitations did you encounter with your method, particularly concerning the balance between coverage, diversity, and false positive rates in the generated data?
In our study, we encountered limitations regarding the balance between coverage, diversity, and false positive rates, FPR, in the generated data from weaker models, WC. While the WC model demonstrated higher coverage and diversity, specifically achieving 11% higher coverage and 86% higher diversity compared to the stronger model, SE, it also resulted in a 7% higher FPR for the math dataset. This indicates that although the WC model can solve more unique problems and provide a greater variety of solutions, the quality of reasoning is compromised, leading to incorrect intermediate reasoning steps despite correct final answers. The mixed signals of high coverage and diversity, coupled with a higher FPR, create uncertainty about the compute optimality of sampling from the WC model versus the SE model for training strong reasoners. Thus, while WC-generated data can enhance model performance, the trade-off with increased FPR necessitates careful consideration in practical applications.